Welcome to Lecture 10. Today we're going to be talking about equilibrium and how to calculate the adiabatic flame temperature. So the first thing to mention as we begin to talk about this is the different types of energy that are in a fuel or any sort of molecule. Thus far we've been working with the change in temperature which is associated with the sensible energy of the molecule. So these are all different types of energies that can be stored in the vibrating of bonds, the spinning of the molecule, the kinetic motion of the molecule, which is actually what we're measuring when we measure temperature, is that the speed of that average kinetic energy of the molecule. There are other ways that atoms and molecules store energy. The next level up is the chemical energy stored in the bond itself, and that's what we're going to be talking about today as we talk about breaking those bonds and burning things. And then there's the nuclear energy, which is beyond the scope of this class. In between those chemical energy and the normal sensible enthalpy of the kinetic motion and the vibration and spinning, the latent energy is something you should be familiar with. That's the energy released as you thaw or boil something. And that'll have a small role when we talk about heating values of the fuel, mainly in whether we consider the latent energy of the water vapor as the water as a liquid or as a vapor, and that determines whether it's the higher heating value. We're going to touch on that again in a bit. So to get some terminology laid down for this discussion, things we want to bring up are the enthalpy of reaction or of combustion. Now this applies for a specific reaction. So a fuel burned in air to completion would have a very specific enthalpy of reaction. And I don't mean specific enthalpy as in enthalpy divided by mass. I mean a given fixed amount of energy will be released for that reaction, and we call that the enthalpy of reaction. The enthalpy of formation is slightly different. Every fuel will have an enthalpy of formation, as will every other type of molecule, and this is the reference value that we add up to find the enthalpy of a reaction. So by summing the enthalpy of formation of the products and separately summing the enthalpy of formation of the reactants, the difference between products and reactants is equal to the enthalpy of reaction. And then sensible enthalpy is everything we've been working with so far. So when we've been doing the change in temperature, the heat in is equal to mCp delta T, or this may have been m times the change in enthalpy. When we've been doing that equation, that is the sensible enthalpy. So this is all of the energy stored in kinetic motion, rotational motion, vibrational motion, and that is the energy as we raise the temperature of something without changing its composition. So to hit on that just a little bit farther, specifically with the enthalpy of formation. So every molecule, O2, N2, hydrogen, they're all assigned an enthalpy of formation. And the enthalpy of formation of monatomic oxygen, so just an oxygen atom, is going to be different than a diatomic oxygen molecule. So every possible molecule has an enthalpy of formation. Now for certain common ones, such as these, the oxygen, nitrogen, hydrogen, and carbon on its own, we assigned a 0 reference state at a specific temperature. So that is a starting point that helps simplify a lot of our equations, because these show up a lot. So a lot of the time in our calculations for the enthalpy of a reaction, the enthalpy of formation of these molecules will always be 0. So for something simple where you're burning carbon in oxygen, the enthalpy of both of your reactants is 0, and the enthalpy here of your product, CO2, is actually negative 393,000. And the way we would do that is, imagine we burned pure carbon in pure oxygen. The energy that is released is equal to negative 393,520 kilojoules per kilomole of CO2 released or produced. And if that's the energy that's released from these two fuels that start with a enthalpy of formation of 0, then the enthalpy of formation of CO2 must be negative 393,520. Okay, so slightly different but related are fuel heating values. So these are related to that enthalpy of reaction. It's not specific to the fuel because the same fuel could be burned in air, and it could be burned in ozone. It could be burned with any other type of oxidant, and the heating value would be different, or the enthalpy of reaction would be different depending on the oxidant used. But heating value, since almost all of the time in applications we're burning these fuels in air, the heating values can be tabulated for combustion with that fuel, specifically in air. Two versions of the heating value exist. The higher heating value refers to the larger number, and the lower heating value is a slightly smaller number. The difference is, if we burn something and the resulting products, they had a significant amount of vapor, but the water was still in its vapor form, that amount of energy that's released while the water stays as a vapor is the lower heating value. If you then extract more energy from that combustion and cool the products all the way back to the point where water returns to being a liquid, that extra energy which is released as the water condenses, that adds to the lower heating value to become the higher heating value. So the higher heating value is so called because it's a larger number, not because it's a higher temperature, but because the quantitative number is higher. So graphically what this looks like is you have some amount of fuel burning with some amount of air, and you have the products, and there's going to be vapor water in those products. That heat release of that reaction is the lower heating value of that fuel. If you then condense the products to the point where the water condenses out as a liquid, there's more energy released here. And that latent energy of the water added to the heating value gives you the higher heating value. So the common way we actually measure the heating values of fuel is with something called a bomb calorimeter. And the idea here is you put a known amount of fuel inside a chamber, and you put a known amount of air in there, so enough that it's going to completely combust. And then you put it in a water bath, so completely submerged in water, so all of the heat will eventually dissipate into the water. And then you insulate your pool of water as best you can. Then somehow within the bomb calorimeter you trigger the combustion, the energy is released, and if you wait long enough, that energy will dissipate out of the bomb calorimeter into the surrounding pool of water. We measure the change in temperature of the water, and we know exactly how much heat was released during that combustion. Okay, let me switch over to OneNote here. Alright, so as an example, let's talk about finding the enthalpy of reaction, or the heating value for combustion of N-butane. So in this case we have a reaction that is C4H10 plus some amount of air, A, oxygen, plus 3.76 nitrogen. Let's keep it simple today and we'll do dry air. And so that's going to go to some amount of CO2, some amount of water, and some amount of nitrogen will be in there. Now, we'll do this for a stoichiometric reaction, so the precise amount of oxygen. We'll find that the heating value you would calculate would be the same for excess oxygen. The heating value will remain the same, but the temperature of those products might be different. Since there's more air you'd have to heat up, with the same energy being released, your temperature won't rise as much. So if we do the balanced stoichiometry here, we find that we get B is equal to the number of carbons, that's 4. C is, 2C is equal to 10, so in this case C is 5. A is going to be 2B plus C equal to 2A, so we get 6.5 in this case. And for nitrogen, for D, we're going to get 24.44. So that's our balanced reaction. How do we now find the heating value? Well, we're going to set up a equation where we start with the enthalpy of formations of the products, so everything on this side, and then we're going to subtract the enthalpy of formation of all of the reactants. So let me see if I can sketch this out here. We'll have the change in enthalpy of the reaction is going to be equal to, on the product side, I have B times CO2, so we have 4 times the heat of formation for CO2, which was negative 393, 520. And then I'm going to add to that the heat of formation of water. So I have 5 moles for C multiplied by negative 285, 830. Sorry, and the units on all of these are going to be kilojoules per mole. I should be writing that. And then for the nitrogen here, we have 24.44 times the enthalpy of formation of nitrogen. That was one of our reference ones. That's going to be 0. So then from that, we can subtract everything on the left side. So we're going to have 1 mole of this N-butane, C4H10. So that's minus 1 times negative 126, 150. And then I'm going to also be subtracting the oxygen, nitrogen. Both of those are going to be 0. But I'll do it here just for completion. 6.5 times 0 and 6.5 times 3.76, which is the 24.44 times 0. So if I calculate this out, 4 times negative 393, 5 times negative 285,000, so on, we get an enthalpy of change in enthalpy for this reaction equal to negative 2,877,080 kilojoules per kilomole of fuel. So that's the other thing that's important to note. This isn't this value, this amount of energy being released is per mole of the fuel. And this is why I like to set up the balance reactions for a single mole fuel. Even if the fuel had two components, 50% one, 50% the other, if we set it up per mole of fuel, then when I do this balance calculation for the heat of reaction, the number I get is going to be correct. So my question here now is this the higher heating value or the lower heating value? And in this case, what I've done for you is the higher heating value, because the term I used right here for the enthalpy of formation of water is the enthalpy of formation of liquid water. If I instead wanted to do this for water vapor, I would have used negative 241,000. And so if you see that number, then this would be the lower heating value. So this number, whenever I'm using 285,000 for water, is the higher heating value. So let me switch back and we'll start going over how to calculate the flame temperature. All right. As you burn something, that energy that's released during combustion is all going to go into the sensible energy of the products, unless there's some heat loss. This is just a simple free body diagram. First law, energy balance. You have the fuel and air might not be at reference temperature. They might be coming in at something like 800 degrees. That energy is going to equal whatever heat you lose plus the heat released from the combustion. All of that is going to add up to the total energy in the products. So when we say adiabatic flame temperature, what we're talking about is when there's absolutely zero loss of energy, so no heat loss. That's what we mean when we say adiabatic flame temperature. So all of the energy of the fuel and air, the sensible energy they start with, plus the energy released during the combustion, all becomes the sensible energy of the products. And you'll see me stick to this nomenclature where you have this reference enthalpy of formation, and then the sensible enthalpy is this difference here between the total enthalpy and the enthalpy at some reference state. So typically all of these values are referenced to 298 Kelvin. So the sensible enthalpy would be referenced to 298 Kelvin, and the difference in enthalpy of formation that you calculate for the reaction was what the energy release of that reaction if it occurred at 298 Kelvin. So let's talk about adiabatic flame temperature, and let's just imagine for a moment what is the highest possible temperature flame. Well, I'm going to start by guessing that it's burning hydrogen in pure oxygen, perfect stoichiometric conditions. There's a lot of energy here to release relative to the mass. But the flame temperature here is it's pretty high. It's 3,079 degrees Kelvin. We've talked about temperatures higher than that for some of our combustion engines, but the difference there was we started with the reactants having already been compressed up to 900 or 1,000 degrees Kelvin. This flame temperature that I'm talking about in this slide is assuming the reactants started at 298 Kelvin. So obviously if I started at 500 degrees, this would be a few hundred degrees higher. Oops. Okay, the actual highest flame temperature might be diacetylnitrile burning in pure ozone. It amazingly has an adiabatic flame temperature of over 5,000 degrees Kelvin, and that's starting from basically room temperature. So why does this reaction, which has so much more mass, there's all this carbon to heat up, and nitrogen, which is much more massive than hydrogen, why does this reach a higher temperature than hydrogen plus oxygen? Well, the answer is because of dissociation. When we burn hydrogen and oxygen, we don't get pure water. What we would actually get if we balance all of the equilibrium species, we'd get about 70% of it out as water, but we'd get some oxygen that didn't burn. We would get a significant amount of the hydrogen that wouldn't burn. Almost 20% of the fuel wouldn't burn. And we'd have some new radical species here. Pure hydrogen that's not in a molecule form, such as hydrogen, basically just protons flying around. We'd have some hydroxyl ions flowing around, and we'd have some oxygen that was at such high temperature that it just split in half. About 4% of that. So dissociation, why does that result in a lower flame temperature? Well, you have a bit more molecules, so the energy can be spread around those more additional molecules. So the kinetic energy is distributed among more species. And then there is, if you imagine this burned all the way to water and then split back into these parts, there's a certain amount of energy required to break those water bonds and result in these species over here. So that subtracts from the energy of the reaction. One of the things we can do to combat that is to combust things at high pressure. So that's helpful to us in an engine, as any type of engine, whether it's a jet engine or a internal combustion engine. We're almost always going to be doing our combustion at elevated pressure. And with Charrier's principle, high pressure is going to basically squeeze these molecules back together, and they would prefer to be in the form of water rather than split into these constituent parts. So high pressure is going to shift equilibrium towards more complete combustion, and that's nice because that's what we would prefer. So let's talk a little bit more about this. If we managed to do it at such a pressure that there was no dissociation, burning hydrogen in pure oxygen would still not exceed 5,000 degrees Kelvin. So it's still not as high as the other flame. And the reason for that is more about the specific heat of the products. So in burning hydrogen and oxygen, the product is a triatomic molecule. And so you can imagine it has this shape that's large and offset. It has a center atom it can rotate around. It can rotate in 3 dimensions. It can vibrate both bonds. All of those add more places you can store energy that are not the kinetic motion of the molecule. So that all of those add to the specific heat. So if I put in a unit of energy to a water molecule, some will go to kinetic motion of that molecule, some will go to these other degrees of freedom. If I put that same unit of energy into a diatomic or monatomic molecule, it doesn't have as many degrees of freedom to store that energy. So it is more of that energy will go into the kinetic motion, and thus the temperature will go up more for the same unit of energy. So the reason why this flame is so much hotter is that the resulting products are carbon monoxide and nitrogen, and they're diatomics. So they're going to have lower specific heats and heat up a lot more for the same amount of energy. The other reason is that they are very stable, so we don't really have to worry about dissociation because those bond strengths are so high between these two atoms. And then the final thing of why this flame temperature is so high is we're not only getting energy out of the fuel. In this case, we're also getting some energy out of the oxidant. O3, ozone, actually decomposes exothermically down to oxygen. So it's like we're starting with a little head start when we start with ozone. It's going to release some energy, become oxygen, diatomic oxygen, and then that diatomic oxygen burns the fuel. So we're getting a little bonus jump start energy there. So how are we going to calculate adiabatic flame temperatures? The first thing to remember is that the flame temperature is not fixed for a given fuel. It depends on your starting point, what temperature you start the reaction at. Second thing it's going to depend on is how complete the reaction is. So this is coming back to that, to dissociation, or what we'd been using previously, how what the combustion efficiency is, how complete the combustion is. The flame temperature will depend on that. The flame temperature will also depend on any excess air that we have, because that excess air won't add to the energy release, but it will absorb the energy and not allow the temperature to rise as much. And then finally, the final products, this is back to related to degree of completion of the reaction, but the final products, they may absorb energy from the combustion event. So let me switch back to the PowerPoint, or to the OneNote, and I'm going to go through the example of combustion of N-butane with 130% theoretical air. So in this case, I'm going to talk about burning C4H10, again just with dry air, so we'll do O2 plus 3.76 N2. And we're going to imagine complete combustion here, so we're still going to go B times CO2 plus C times water plus D times nitrogen. But this time we might have some excess oxygen, so I'm going to include that there. And for this problem, we're going to try and burn with 130% theoretical air, and we're going to assume the reactants are at 900 degrees, 900 Kelvin. So what do we need to do here to solve this? Well, what I've posted to the website is a Excel sheet called adiabatic flame temperature, and there's two sheets here. The idea is you're going to put in the first sheet what your reactants are, and in the second sheet we're going to put the products. Apologize, in this one I haven't actually put N-butane in, so let me switch this up and let's just start with methane. I think I have this set up, so let's go back and rewrite our problem here. We're not going to burn N-butane, we're going to burn CH4, regular methane, the main constituent in natural gas. So if we were to balance this stoichiometrically, in this case we're going to, how much oxygen are we going to need? Well, we're going to need one oxygen to burn the carbon, and we're probably going to need one oxygen to burn that hydrogen. So A, at stoichiometric conditions, is going to be 2, and then at 130% theoretical air, that's going to be 2.6. How much CO2 are we going to get? We're going to get B is equal to 1. How much water are we going to get? We're going to get C equal to 2. And then the nitrogen is going to be equal to 3.76 times 2, or times 2.6. And the amount of excess oxygen is going to be, let's see, we have 2.6 oxygens on this side. There's going to be 1 in the CO2. There's going to be 1 in those 2 molecules of water. So the leftover is going to be 0.6 moles of oxygen. So let's see what happens when we start those at 900 degrees. So in this table, I'm going to start on the reactants tab. I'm going to start the reactants at 900 degrees. And I'm going to imagine here I have 3.76 times, we had 2.6 for A, And here for oxygen, I'm going to go 2.6. And that was burning 1 mole of methane. So this table breaks things down for us and gives us exactly what the molar composition is of our reactants. So we have 73% nitrogen, 19.4% oxygen, and about 7.5% methane. It's also going to calculate the enthalpy, the sensible enthalpy at 900 degrees for this for each species. So there's 18 kilojoules per mole for the nitrogen, 31 kilojoules per mole for the fuel. And down here in the orange is going to be the average sensible specific enthalpy for our products. So that'll be 19.39 kilojoules per mole, and it looks like in total we have 13.376 moles. So if I multiply those two things together, I get the total sensible enthalpy of the reactants. This next column here is the enthalpy of formation. So for each individual species, there is some enthalpy of formation. Those are going to be constants that will multiply by the number of moles, and we get in the orange basically the enthalpy of formation per mole of reactants, and down here below the total enthalpy of formation for all of the reactants. Now the way that we're going to find adiabatic flame temperature is we're going to go over to the products tab, and now we're going to put in the products of combustion that we have. So we're still going to have the same amount of nitrogen, 2.6 times 3.76. We're going to have a little bit of extra oxygen, so that was 0.6. We're not going to have any hydrogen. We're going to have 1 CO2, and there's going to be 2 waters. So in this case now, the enthalpy of formation for these products of combustion are different. Now we have 877, negative 877, and the reactants were negative 74. So the difference, if I do products minus reactants, that difference is, I don't know what that is, 877 minus 74 would be somewhere about 803. That's how much energy is released from the reaction. And I started with, in the reactants, I started with 259 kilojoules of energy, and I'm going to release that 803. So that's why the products here should be that 259 plus 803. This equation, the difference should add up to the total sensible enthalpy that I should get when the combustion is ended. So what I'm going to do is I'm going to adjust the temperature of the combustion until I get the correct sensible enthalpy. So this is what I should get. The enthalpy of formation of the products minus that of the reactants plus the energy of the reactants should be the energy of the products. So it looks like I'm a little high. I'm going to try 2200 degrees. That's a little low. Let's try 2300 degrees. 983, not quite there. 2400 degrees. 1038, now we're getting close. So let's try 2430. Still not quite there. 2445. A little too far. 2442. Whoops. 1061.59, so now we're really close. 2442.3. All right, now we're right about on it, down to the third significant digit, or at least that. So we've got 161.70, so it's somewhere around 2442.25. Looks to be pretty close. Maybe somewhere around 42.22. Yeah, there we go. We're looking pretty close at this point. So this is how we would find the adiabatic flame temperature for burning methane in 130% excess air, assuming, remember this is all based on the reactant starting at 900 degrees. Okay, so when we walk through the steps again for finding adiabatic flame temperature, you're going to start with the temperature of your reactants, and you're going to put in all of the moles of your reactants. That's going to give you the total sensible enthalpy of your reactants, and it's going to give you the enthalpy of formation of your reactants. Next, you go over to the product side, and you're going to need to put in all the moles of your products based off your balanced stoichiometric reaction. That's going to calculate the enthalpy of formation of the products. At the top here, this target sensible enthalpy is the energy of the reactants plus the enthalpy of the reaction. The enthalpy of the reaction is the difference between the product enthalpy of formation and the reactant enthalpy of formation. So we get this target number for the target sensible enthalpy of the products. Down here in cell F22, this is what the sensible enthalpy of the products are at the temperature in my yellow box in the upper left. Now I'm going to adjust that temperature until that value in F22 matches the target in E1. And that's how we'll find the adiabatic flame temperature. Alright, with that, I'll conclude this lecture and